My name is Stollnitz, and I'm going to show you how we can get started creating an AI-based rock, paper, scissors game. The code I'll be demoing uses my webcam to capture an image as I make a rock, paper, or scissors with my hand, and uses AI to classify that image. In fact, if you watch the AI show, you may already be familiar with the Rochambeau app that I'll be showing you today. There are three major parts in the development of this app. In part one, I'll show you how I can train and test a machine learning model that classifies the images locally on my machine. In part two, I'll show you how to train and deploy this model in the cloud using Azure ML. And in part three, I'll show you the web app that gives us a user interface to interact with the trained model. Let's start with step one, where we'll be training the model locally. We're using a pre-trained ResNet 18 model. The inputs to our model are images that look like this for rock, this for scissors, well, you get the idea. And the labels for the images come from the name of the directory where they're located. We're using the PyTorch deep learning framework, the PyTorch Lightning package to reduce the amount of PyTorch code we need to write, and the MLflow open source package to log some parameters and metrics. I'll show you later how to look at these logs. We can run the training code by choosing the PL trainer launch configuration and pressing F5. Training takes a few minutes, so I use the magic of video editing to skip forward to the final result. You can see here that training was done over 7 epochs and achieved a very low validation loss and a validation accuracy of 1, which is perfect. We can look at our MLflow logs here. For example, let's look at our validation loss over the training epochs. Or instead, we can look at the nice UI that MLflow provides us to see the same information visually. I always like to test my models locally before I train them in the cloud, which we can do in this app by running the PL tester launch configuration. This tests our model using just a few images, so it should be pretty quick. And as you can see, our test loss is also very low and our test accuracy is 1. This is great. We're ready to move on to step 2, where we'll train and deploy our model in the cloud using Azure ML, which gives us the opportunity to use more compute and work with bigger datasets. This step will require the creation of several Azure ML resources. I have 3 options to create these resources. I can use the Azure ML Studio UI, I can write code using the Python SDK, or I can use YAML files in the Azure ML CLI, which is what I'll do for this demo. Let's look at the YAML file containing the configuration for my data, which, as you can see, points to the location of my local data folder. I can upload this data to the cloud and create the corresponding Azure ML data asset by invoking the azml data create command in the CLI. Let's verify this using the Azure ML Studio. And there's our data asset. We need to create a few more cloud resources for our scenario to work. We could create each one individually in the terminal as I just showed you, but instead we created a GitHub action containing all the CLI steps, which makes them much more easily reproducible. The GitHub action creates a job that runs my training Python file in the cloud, then it downloads the trained model produced by the job, then it registers the model with Azure ML, and finally it creates a deployment and endpoint we can use to query the trained model. Let's run it. I'll fast forward here, and when it's done, we can go to the studio and take a look at our training job. You can see here nice visualizations for the MLflow parameters and metrics we logged earlier. We can then go to the model section and see that our model was indeed registered in Azure ML. And finally, let's verify that our endpoint was created. And it was. Great. Now let's test the endpoint. Our input section is already populated with a test image, and our prediction is scissors, with really high confidence. Excellent. We're ready to move on to step 3, where we'll query our endpoint from within a web app. We're using an Azure static web app here, with an Azure function that does a post request to the endpoint we just created. Let's look at the web app running. I'll capture an image, and then I'll submit it. This triggers a post request, which passes the image I just captured to the endpoint and gets back a prediction, rock, which is correct. And that's all there is to it. We're well on our way to writing a rock, paper, scissors game, and machine learning has made it so much easier. Thank you for watching.